In this video, I'd like to show you how you can combine some of your knowledge about trig functions with what you're learning currently about parametric equations to make some interesting animations. So here we have a picture of baby Yoda, and he's at the coordinate 1, 0. And what I'm going to do is I'm going to try to modify baby Yoda so he follows the path of the unit circle. So I'll do this by changing the center on the image there. Instead of 1, 0, I'll set the coordinates at cosine of t, sine of t. So we remember those as our x and y coordinate on our unit circle. And I'll add a slider for t, letting the parameter run from 0 to 2 pi. And I'll just make the step rather small, maybe 15 degrees or pi over 12. And as I animate this, what you're going to see is you'll just see baby Yoda trace out the path of the unit circle from 0 to 2 pi. And this should make sense from what we're learning about parametric equations, because if x is equal to cosine t, then that means x squared is equal to cosine squared. And if y is equal to sine of t, then that means y squared is equal to sine squared. And of course, then if you put x squared and y squared together, you're going to get 1. You're going to trace out the path of the unit circle. Of course, but we can make a few maybe small modifications to this and think about having baby Yoda follow some different paths. Look at what happens when I let the x-coordinate equal sine and the y-coordinate equal cosine. Now we see baby Yoda starting up at 12 o'clock, and he's actually moving in a clockwise fashion instead of a counterclockwise fashion. This is because when I eliminate the parameter, I still get x squared plus y squared equals 1. I'll still trace the path of the unit circle. However, the place that I start and the direction that I go is a little different. That's because the x-coordinate is following along the sine curve, which starts at 0, and the y-coordinate starting along the cosine curve that starts at 1. So you can continue to make little modifications, like you can think about starting with negative sine as your x-coordinate and keeping the y-coordinate as cosine of t, which of course is just going to make him go in the opposite, back into the counterclockwise direction, but still starting at 12 o'clock. And you can think of all sorts of little modifications that you can make from there. In fact, let's take a look at what happens when I change the amplitudes of the sine and the cosine curve. If you make them each equal to 2, then what's going to happen is he's just going to trace out a circle with a radius of 2. That should be no big surprise, because when we think about the x as a function of t and y as a function of t, the sinusoids that he's tracing along have an amplitude of 2. You could think about all sorts of other modifications that you could do. What if you stretch out cosine more than you stretch out sine? So maybe 1 sine for cosine for the x-coordinate, and then 3 cosine for the y-coordinate. You see what's happened now is I've made baby Yoda follow along an elliptical path. And the reason that he follows along an elliptical path, he's more or less following this path right here that I'll try to trace out with my pencil, like that. The reason he's following that path, well, sure, it's because I stretched out the cosine, which is the y component, but we can still think about trying to eliminate the parameter in the same way we did before. If x is equal to sine t, and y is equal to 3 cosine of t, then I can say that x squared is equal to sine squared, and I can say y divided by 3 squared is equal to cosine squared. So now I end up with the equation x squared plus y divided by 3 squared is equal to sine squared plus cosine squared, which is equal to 1. And this is the equation of an ellipse rather than a circle, because the coefficients on the x squared and the y squared terms are different. So you could continue with that kind of manner to make Yoda trace out all sorts of different kinds of paths. In fact, you might even be curious, what else can you do? What other kind of knowledge about sinusoids could you try? What if we went back to coefficients of just 1, but we thought about how do you make Yoda trace out a path that isn't centered around the origin? Maybe you'd like to center it around a different point. you can see that I can shift the sine coordinate, the x coordinate over without shifting the y. And now Yoda's tracing around a path that is centered here at the point 1, 0, because I've moved the x over by 1 and I didn't make any alterations to the y. And it keeps the radius equal to 1. And we can see algebraically why that would work. And I think you can see algebraically why that would work, because if x is equal to sine of t plus 1, then that means that x minus 1 is equal to sine of t, and thus x minus 1 squared is equal to sine squared. Meanwhile, y is just equal to plain old cosine, so we can conclude that y squared is equal to cosine squared. And anytime I have that sine squared and that cosine squared, I know from my Pythagorean identity that I can add them together and get 1. So that means in this particular case, I can add together x minus 1 squared plus y squared to equal 1. So if x, let me put that back there, if x minus 1 squared plus y squared equals 1, then I can understand that that is still a circle, but the x component of the circle has been shifted right 1 unit, exactly as my parametric equation implied. Let's think about maybe 1 or 2 more little modifications that we can do with trig functions. See if you can guess what will happen here if I switch back to cosine first and then sine first. But instead of keeping the frequency equal to 1t, what if I try 3t, cosine of 3t and sine of 3t? What will happen here is as I trace the parameter t from 0 to 2 pi, you'll see Yoda do 1 trip around, here's the second trip around, here comes the third trip around on the standard interval from 0 to 2 pi. So in a sense now Yoda is going 3 times as fast as he did before. Okay, so does everything that we do with trig functions automatically make circles? Not necessarily. Really, trig functions just allow you to oscillate back and forth. What if I were to do sine of t as my x-coordinate and cosine squared of t as my y-coordinate? What kind of path would he follow here? Well, what you'll see is this will make Yoda do a little hop dance from the left, from the right over to the left and back. He's just kind of hopping back and forth between 1 and -1. And if that looks like he's tracing out the path of a circle, I'd like to just quickly convince you otherwise. If we have that x is equal to sine of t, then that implies that x squared is equal to sine squared. Meanwhile, y is equal to cosine squared of t, so no need to square anything here to get our Pythagorean identity. What I can conclude from these 2 bits of information is that x squared plus y is equal to 1, which means y is equal to 1 minus x squared. So what he was doing there was just hopping along a little part of a parabola that was opening downward with a vertex up there at 1. Okay, I hope you like my little video with Baby Yoda, and this gives you an idea of how you can impart some of your knowledge about trig functions into what you're learning about with parametrics.